Okay, so this is the absolute best advertisement for Apple products. So thank you for that. Okay, good afternoon. I'm going to fly you through this now because we lost 20 minutes. Welcome to my talk, Take Back Control of Your Data with Event-Driven Systems. So my name is Henrik. I'm an independent consultant from Norway. And I'm here today to talk to you about how we built a completely new customer data platform for a company with the largest customer base in Norway. And the client in this case was and still is Norsk Tipping, which is a state-owned gaming company in Norway. And with more than 2.1 million active customers, Norsk Tipping has more than half of the Norwegian population aged 18 or above as active customers. And this is one of the reasons why they wanted to modernize their customer data platform. So this right here was the problem statement. We need to build a modern and resilient customer data platform. But before we talk about the new stuff, we need to consider how things were when we first started. So the company had all their operational data in one large monolithic database with hundreds and hundreds of tables. All of these tables were built with sequences and foreign keys and custom composite views and a huge amount of custom SQL functions. There were domain-specific tables made by a naming convention. So all the customer data were in tables called CST_. But other than that, there was a free-for-all in regards to reads and writes to the database. And since all the operational data was stored in this one single database, there were lots of talk about performance issues. And I need to state that there's never been, as long as I worked there, actually any performance issues with that database, but there was a whole lot of fear about having such issues. So an example, if we wanted to introduce a new database table, there were always lots of questions of why we really needed to do this, because there was fear that it could slow down the database and ruin performance for other parts of the organization. So in short, this is of course not an acceptable way to deal with performance. So we wanted to build a new and separate customer database or a customer system or a customer data platform, which should not be a part of this monolith. And the new database needed to at least aspire to having future-proof data representation. It needed to be expandable for complex objects like names and phone numbers and addresses, because we don't know what will happen in the future. And the system was supposed to be event-driven. So in a traditional database-centric system, most tables and entries in tables are designed to contain the current state of each entry stored in the database. And we see that a customer has an ID, and if we wish to update that field, then that single column on that specific record gets updated, and the history of that, what that column previously contained is basically forgotten. So designing and implementing a system using this approach with the CRUD operations would be a fair task. However, this design does not necessarily give us as users the best insight to what data was changed and by whom. And also, it's also known as audit logging. So one small disclaimer, most databases have such logs available, but it's not public APIs for us users. So also there's no way for other stakeholders or applications to react to this update as the change is not published anywhere. So to reiterate, the database approach has one record per customer, it has no easily accessible changelog, and it's difficult to have accountability for who made changes to the data object, and the changes are not published. So we wanted to go with an event-driven system, but what is an event-driven system? An event-driven system is where each significant change in the data object produces a change event that gets published for the world to see. So all the stakeholders or system that could benefit from this information. So here's an example of an event. The data object email gets modified, and the modification event gets published for everyone to see. And we can look at an event-driven system like this mathematical statement, where all changes to data are a result of an event being applied to the previous state of the data object. So in this example, the sum 8 is the result of adding the three numbers 3, 2, and 3 again. Our initial state is 0, we have nothing. Then we add 3, we add 2, and we're at 5. And then we finally add the last 3, and we get to the current state 8. So we can see that each individual operation is a part of a chain of operations, and that they together tells a story of how we got to 8. And because there are more ways to get to the state of 8, the story can also be significant. So this chain of operations will also get the same state in the end, but the story of how we got there is quite different. And conversely, we can use events to build the state object by processing them. So each event is an operation, and after that operation has been applied to the current state, we get a new resulting state object. So first, we create the customer object and get an ID. So the initial state before this first event is null, and then we add a name, we set an email, we add an account number, and then we update the email once more, and we have arrived at the current state of this customer. So as a part of the business strategy to become more event-driven, Norsk Tipping started to invest in Apache Kafka as a part of their technology stack. And everything that we have built and everything that I'm showing you here today is built with Kafka. But the concepts that we are discussing today is in no way dependent on using Kafka, as there are multiple other technologies that could basically do the same thing, or you can use it to build a similar system. So for those that doesn't know, what is Kafka? Apache Kafka is a highly scalable and distributed messaging system for real-time streaming data. It provides high throughput and low latency, which makes it suitable for large-scale operations. Data written to Kafka is stored durably because everything is replicated across multiple nodes, or as it's known in the Kafka world, brokers. And Kafka uses a publish-subscribe model to allow producers to publish events and subscribers to or consumers to subscribe to them to fetch relevant data. And the general architecture of the platform that we built can be split into 3 parts. We have the API layer at the top, we have the core system in the middle, and we have some consumers at the end. The rounded rectangles in this figure is applications, and the pipes represents a Kafka topic that can be read or written to. So we will start by taking a look at the core system. So the core system consists of 4 different elements. We have the input topic, or the command topic. We have one Kafka Streams application that processes commands, creates events, and generates new state objects. And we have an output topic where these state objects will be placed. And finally, we have a result topic that is used for synchronous communication to inform whether or not a command was applied to a state or not. Our schema consists of 4 different objects. We have the input, a command, we have the throughput, an event, and we have the output, which is the state, the aggregated result, and in this case, a final customer. And we have a metadata schema containing just meta information. So a command, the schema object represents the desire to change something, and we place them on the command topic to request a change on a customer. So the change is not guaranteed, it's a request, we wish to do something. Every command is named as a verb in the present tense, because we want to do something, we want to create a customer, we want to change an email, we want to remove a phone number. And the command object, together with the current state of our customer, is what will be validated to see if we actually can perform this request or not. And we will see an example of that. So this is just an example of the change email command. It's an Avro schema. So then we have the event. So when a command has been validated and accepted, it will generate an event. The event object contains the data that will be updated, but it also contains the code that will be performed on the state object, and we will see that later. Every event is written in the past tense because we have to accept an event as a truth. So it's a customer created, email updated, or phone number removed, because something has already happened. So you can see this is the schema. It's basically the same as the command. Then we have the state object. The state object represents the customer at that given moment in time. But since every event will generate a new customer state, there can exist multiple versions of a customer on a timeline. And we need to consider that. And I'm going to show you an example of that later. In some cases, it is advantageous to store every intermediary state. But in other cases, we will only care about the latest known state, and we will discuss these two differences later. Every state object also has a state key that identifies that unique state, and we will see how we can use that to prohibit race conditions. So this is an example of a customer. You can see it has a customer ID, it has a name and an email. And finally, the metadata object is what tells us who did what, when, and why. So it answered that very, very important questions of who actually made a change to the customer. So we can just see here, the command comes in, we have an event in the middle, and finally we get an aggregated state. Norsk Tipping, they has decided to divide their technical resources into different teams, and each team has one or more business domains that they own. And the team that I work for has one responsibility, the customer data. But with that responsibility, we also have to provide APIs for other teams to be able to do their job. And with that, we need to discuss what's called a projection. So a projection is a copy of existing data that has been processed or formatted to serve a special purpose. So a projection can live within the source domain, or it might live outside it. And we have two examples of projections. We have an application called Customer Lookup, which is a service that we, in my team, built that consumes the source topic and stores the latest known version of a customer in a relational database. So this service has been created to make the data queryable and fetchable. So for example, you can answer the question, please give me every customer named Henrik and that lives in Oslo. But this service will never store any historic data, but that's not its purpose. And we can see that one of the benefits of having this projection is that we can get powerful queries, but it's slow to read and slow to write. Customer history, on the other hand, is a service that consumes the source topic and stores every intermediary state. So this service is created to let us fetch the customer history and see how an event actually modified the customer from the previous state. So this service is not indexed to make the data queryable, like in Customer Lookup. It's not that service purpose. So the benefits of this service is that it has a very quick reading and writing from the source topic, but the con is that it needs to store huge amounts of information, and we cannot do any complex queries. This service can only answer the question, fetch me this customer history by a customer ID. But what do we do when data crosses the boundaries of our domain? So the customer domain team, in this case my team, we will expose some APIs for other teams to consume. And an API might be a trusty old web application with REST-like endpoints, or it might be a Kafka topic that other teams can consume. So a real-life example of this is that the identity and access management team at Norsk Tipping, they will consume data from the customer's state topic in order to create their own projection with data that's relevant during a login. So for example, the customer status. So a customer needs to have a status of active in order to actually log into our services. And it's kind of important to understand that providing this stream of data that makes the IAM team able to make changes to their own projection in real time is what makes this technology so powerful. Because since we have thousands of login requests every minute to our services, it's important that the IAM team can create a copy of the customer data that can live close to their application and not in a slow relational database in another team's domain. So they can create a projection that solves their specific use case in the best possible way for them. Finally, we're going to take a look at the command API. This is an application that serves a REST endpoint where you can request a change. This application will then place a message on the command topic and wait for a reply from the result topic. So a calling client, for example, our native apps will call the command application. Then they will try. The application will try and actually do the command, and it will get a result and send that back to the calling client. And now we're going to do a demo. So Let's hope this works, because I need to change the screen. This is ridiculous. I need help again, guys. Yes, nice. Okay, thank you so much. Okay, we're going to start by looking at some code. So we're going to look at the customer state processor, so the core of the system. So customer state processor is just Kafka Streams application. Kafka Streams, very simplistic. It consumes a topic, performs some transformations, and might produce an output to an output topic. So we can see here that we are reading a stream. We are reading from the command topic. Then we're doing a transformation. And then finally, we are sending the state events to the output topic. So we're going to jump into the transformer and take a look at that. So for each and every command that enters the application, we get the customer ID for that customer or for the request. And we will fetch the current known state of that customer. Then we have two validation functions. So we have one command that requires that the customer does not already exist. And that is the command create customer. So we have a function called require no existing customer. And then for the rest of the commands, we actually require there to be a customer. So we have a helper function called require customer. Finally, then we will do some general validation of this command. And then we will decide, depending on what type of command it is, we will perform an execute function. So we have a change email in this example. We will check that this requires a customer. We have the customer, that's fine. Then we will perform the execution. So we will try and execute this command. So first we will validate, can we actually perform this specific command? So in this case, I created a very, very simple email validation service that validates if this string contains an @ sign. I promise you, this is not what we're doing in production. This is just for this demo. And when this command has been validated, then we will do a comparison. We will fetch the current email on this customer. We will create a new email object with the inputted email. And if these two are equal, then we will just produce an empty list. Because there was not a change. There's no change in this command. The email is still the same. And we will only produce an event if there is a significant change in the data object. So if the aggregate, the current state of the customer, was null, and we get a new email in, we will create an email added event. If we had an email, but the new email is changed, we will create an email updated. And finally, if we had an email, but the input email is blank, we will have an email removed event created. So in this test, we're saying that we got an email added. So we get a list of events. So in this case, only one event was produced. So we will do a fold, which is like the mathematical function we had. We will start with our initial state, which is an active customer. And we will apply each event logic on that state. And for each event, we will produce a new state, and we will just jump forward. So in this case, we only have one, so we'll take the current state of the customer. We'll perform the apply function, function for email added. And this is just really simple. We just take the new email and we set it on the aggregate. Just replace it, of course. And by building these extension functions, we make the code really easy to build and test, because this is where we do all the data modification. It only happens in an apply function. So we have total control that when we have an email added, this is what's happening, nothing else. And with that, we're going to try and do some requests. So I have the system running now on my machine. Hopefully, I had to reboot. So we will test it. So I will try and place a create customer command. And we can see that I got back a new customer ID with a new state key that represents this state. So I can now try and fetch this customer, and we can see that we got this customer with 97. The customer ID starts with 97. It has a status of created, so this customer is not active yet. We have no phone numbers, no addresses, no names, no nothing. We don't know anything about this customer yet. And then we can try and add a name. So we'll do a change name. We can see that we're still on the same customer ID. So it starts with 97, but we have a new state key with the 444s. You can now try and fetch that customer again. We can see we have gotten a name, and we have the state key of 444. We can try and... no, we can't. Please give me some internet. Okay, we can try and add an email. We can see that we got a new state key. I'll try and fetch that once more so we can see that. Yes, we have an email. And then I can add some more data here, an address, a phone number, add a gender to the customer, and I can finally change the status to active. I can fetch this customer now, and we will see that, okay, I have a customer. So how do we utilize this in our day-to-day operations? So we have created just a basic tool. I've created this tool for this demo, so this is quite a bit simpler than what we're really using. But now I can fetch this customer, and I can take a look at the customer's data. But what makes this powerful is that now I can fetch the customer history, and I can get all the existing states of that customer on a timeline. So I can load the history. And we can see that at 14:41 today, we started with a customer created. And then we can inspect that event. We can see that this event contained the ID of the customer and the status that we wanted to have, the initial status. And we can see that our initial state was an empty object. And we got a customer containing the customer key, the status, and 2 empty lists for phone numbers and addresses. And then we can see that I added a name. And we can actually see the difference between these 2 states. We added a name object with a first name and a last name. And we can just keep continuing up here. We added an email. We have a phone number that we added. We have an address that we have added. We added the gender. And finally, we updated the customer status. So we can now see that we have updated the customer status. Now I'm just going to try and change something. So I will try and change the email. So we will do new email. We got a new state key. So now the state key is EC. We can see here that the state key for this customer that I'm looking at right now is 21, so it's not the correct one. I can refresh. And we see that we have the new state key down here, and we have the new email. And we can also load the history. And we can see that the email has been updated from henrik@modio.no to new.email@modio.no. So, okay, we're closing in, guys. Input validation. So I want to show you how the input validation actually will work. So hopefully my requests will load. Yes, they will. So in this case, I'm just trying to set the email to something without the @ sign. And we see that this command failed. And what is actually happening here right now? The customer command application will place a message on the Kafka topic, the command topic. Customer state processor will read that, try and validate it, and deny that command, and we will place that denial on the result topic. Customer command will wait for a response for up to, I think it's 5 seconds or something like that, and then it will return that error back to us. So we can actually, even though we're doing asynchronous data processing, we can get a synchronous response. Finally, we need to consider the state keys. So right now, I can try and update the bank account number for this customer. We saw that I got a new state key back. And the reason why I could do this is because I didn't say which state key I wanted to perform this command on. But what I can do is I can prohibit race conditions. Because a real-life example, in Norway, if you no longer own your bank account, the banks will send us a notice. Hey, this person does no longer own this bank account. And then we will react to that and remove that bank account number from the customer. But these are asynchronous events. So what if our customer has changed their account number just right before we got that event from the banks? So what we're doing is that we're fetching the customer and matching the account number. So okay, they say that the account number that ends with 5 no longer is owned by this customer. So then we will take that state key, which now is this 9b state key, and we will say that we want to remove that account number from that state key. And we will get a new state. But at the same time, maybe the customer is changing to another account number. And if we try to now change that account number on that previous state, the command will fail because the underlying customer has actually changed since you tried to perform this request. And I think I'm going to stop there. We are right on time, but I would hope to have some questions because I love questions. So are there any questions? I flew through this, I'm so sorry. I had more things. Yes, there's a question on row 3.
I have a similar event-driven system, and is curious about how you handle sensitive data in your stream.
Yeah.
That for the GDPR as laws.
Yeah. So in this demo version that I have here with me today, I don't do any consideration about sensitive data, but in production today we have a 7-day retention in Kafka, which means that after 7 days, everything will be deleted except for the last known state. So we're using the compaction. So we're compacting it after 7 days. And we're sending messages to our consumers about when a customer should be anonymized, when the customer has been terminated, and finally we will send a tombstone to actually null it out. So one problem with that is that we are actually placing some of the burden of cleaning up data on our consumers. But this is it's all in-house, and we have very, very strict access to customer data from Kafka, which means that my team, we are always guiding people to how are you supposed to consume this topic, what are you going to do when an anonymizing event arrives, what you're going to do if you get a termination, and what you're going to do when you get a tombstone. So we're following up all our consumers. Did that answer your question? Or? Anyone else? Yes.
Asynchronous behavior so that you don't have to rely on like a REST answer to be available like in 5 seconds or something like that?
I'm not sure if I understood your question. So the question was, I believe, why are you trying to combine synchronous and asynchronous. Okay, so the customer command application, for example, yes. So we get customer data from multiple different sources, for example, from the banks, but also from the government. If someone decides to change their name, we will get updates about that. And these are asynchronous events. It just happens in the background, and we want to just push that on a Kafka topic and actually perform the change on the customer. Because we don't want the customer themselves to go in and change their names. It's automatic. But customer command is for all the data that we want the customer to update themselves. And I can imagine that you would be pretty furious if you try to update your email. The UI said, yes, it's updated, and it never got updated at all. So next time you started the application, it will just say that, no, it's not updated. So that's why we're combining synchronous and asynchronous. So we want to give the calling client a response. Did this go well or not? Could you actually perform this change or not? So that's why we're doing that. Oh no, we haven't even tried that. Any other questions? Okay, thank you so much.